All right. This unit, we are going to be doing transformations of graphs. So if you remember from past math classes where you might take like a quadratic function, you know, it's a parabola, it looks like a U, and you might rotate it, stretch it, flip it, shift it left to right, up or down. And you've talked about how that changes the equation of the function, how it might change the shape of the function. That's our goal for this unit, is to be doing transformations. Before we can get there, what we're starting with today is some notes on the most basic functions, which we call parent functions. We're going to review their shapes and their key pieces of information. That's what we're doing for the first part of class. And then for the second part of class, I will be giving you some graphs that have been transformed, and we'll be identifying what their beginning graph was, meaning what was their parent graph, and we'll be identifying features of the graph, like a vertex or its domain and range, and things like that. Okay, so that's our end goal for today. So we're going to begin here with these notes, which is just reviewing the basic shapes of the most common functions or parent functions that we're going to be working with. So if you are taking your own notes, what I want you to focus on is not necessarily drawing yourself a perfect grid. Just give yourself an XY and then estimate where the points go. And as long as you have the basic shapes down when you're done, that's going to be good. So don't try and make your notes super perfect. You'll just be frustrated. Just make it good enough, okay? You can always go back later and make fresher, better notes if it bothers you. So those of you who are in class, we're starting with the pamphlet, the little booklet that I gave you. Okay, that's what we're doing first. So we have 6 functions that we're going to review: the shapes, the points, the XY points or ordered pairs that go on them, and also talk about the domain and range and some other things. And on this first slide, the first 2 that we're going to be looking at are up here. This is the name and the equation. So the first one on the left is the identity function, and the equation is f of x equals x. What we're going to do is fill out this XY table and then put those points on the graph and sketch out the shape of the graph. So, because it might have been a whole long time before you did graphs, you know, spring break's been really long. Let's review real quickly what I'm asking you to do, okay? So I have this table with x's all the way down, -3, -2, -1, blah, blah, blah. And the right side is asking me to fill in the f of x. Remember that f of x is function notation? It's equivalent to asking what y is when x is those values, okay? So this equation up here is the same as y equals x, or f of x equals x. If I were to put -3 in for x to this equation, it would give me what for y? -3, right? Because y equals whatever x is. The name of this function is the identity function, which makes sense because it's equal to each other. And so if I just keep putting all those other x's in, when I plug in -2 for x, I get -2 for y. -1 gives me -1, and then 0, 1, 2, 3. And what I want you to do is take a minute and plot those points and then connect them to make the shape of your graph. So like -3, -3 is here. -2, -2 is here. So finish out your points and then connect them for the shape of your graph for this function. So those are our points. And then when you connect them all, you notice that you have a linear function here. And always put arrows on your lines to show that it's going on forever, okay? So this is the identity function. Whatever x equals, that's what y also equals. And then below that, it's asking for, and I have filled this in on your notes this year just to save us some time, but I do want to talk about it a little bit for a second, even though if you're looking at the notes online or in class, it's already filled in. The domain, remember, is the x values that have points on the graph. And in this case, it's all x values anywhere. So the domain is negative infinity to positive. And the range is that as well. And then the intercepts mean the x and the y intercepts. So it's actually asking you for two things, x and y intercepts. And that's wherever the graph crosses the x-axis and wherever the graph crosses the y-axis. And so in this particular case, the x-intercept is 0, 0, and the y-intercept is the same. And end behavior means how is the graph behaving at the far ends as it's going out into positive infinity and negative infinity. How is the graph going? Another way of describing this you might have heard in past math classes is as x goes to positive infinity, what is y doing? And as x goes to negative infinity, what is y doing? Basically at the very ends, is it going up or is it going down? And what I'm going to put, what I normally ask my students to do, and I'll write this down and then I'll explain it, is this. Just some arrows. Like this is a good enough answer for me. But let's interpret that for a second. The arrow on the left is the left end behavior. And the arrow on the right is for the right end behavior. So the left end behavior is this part of the graph. As x goes out to negative infinity, the behavior of the graph is that it's going down forever. And so I have a down arrow for left end behavior. And then on the right side of the graph, as x goes out to positive infinity, the behavior of the graph is that it's going up. The y values are increasing. And so I have an arrow, my right end behavior arrow is pointing up. And what we're going to do for the next 10 minutes or so is finish out these graphs. We have the absolute value function next here. And then we have 4 more after that. So that I can stay on pace with everybody who's in Zoom that might be taking your own notes, we'll do these together 2 at a time. So we've already done the identity function, and I want you to take a minute and finish out the absolute value function right here. Plug in the x values, figure out what the y is, plot them, connect them for the shape of your graph, and then figure out domain, range, intercepts, and end behaviors. Take a few moments for that. Okay, here's what I'm hoping you came up with for your absolute value graph. So remember when we talked about absolute value earlier in the year, we said that it's the distance of a number from 0. And distance is always positive. So if I put -3 into the absolute value equation and perform the absolute value, so I say, okay, What is the absolute value of -3? The answer is 3. Similarly, if I put in -2 and take the absolute value of it, it's +2. -1 gives me 1, 0, and then 1, 2, 3. And the shape of this graph is a V. So we have -3, 3, -2, 2, blah, 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 points, 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 circle, 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 repeat, repeat, repeat. So basically what happened is every point that was negative in the first graph, on the left in the quadrant, in the third quadrant, every y value that was negative is now positive. So it flips up over the x-axis and makes a V now. And this is your absolute value, the shape of the absolute value function. Oh, shoot. Where's all of our time go? Oh, I took forever getting everyone in, sorry. And the domain, range, intercepts, and end behavior are on in your Google Classroom. Those of you in class, it's already printed on your notes because I was trying to save some time. So I want you to please, you can find that later to finish out your notes. I'm sorry I didn't have it on the screen. This is my slides from last year. Mostly my biggest concern for today was that we go over the points and the shapes. So I'm going to leave the bottom section for you to finish later, or at least look at. Okay, so here's the next two functions. We're going to do the cubic and the square root function. For the cubic function, we have x cubed. And notice that the x values are different. That's by design. They have been custom chosen for this function. So x is -2, -1, 0, 1, 2. If you plug those in to figure out what the y values are, just as a quick reminder, if you're plugging -2 into x cubed, it means -2 times itself 3 times. Well, the first two -2's give you +4 times the third -2 is -8, right? So -2 cubed is -8. -1 cubed then is 1 times 1 times 1, which is 1. Tis not 3, right? And will still be negative because you have negative times negative times negative. The first two cancel out, making a positive. But then when you multiply by the third negative, it becomes negative. 0 cubed is just 0. 1 cubed is 1. And 2 cubed is +8. And so here's what the shape, so we're going to put those points on our graph and see what that shape looks like for a cubit, okay? -2, -8 point is way down here. -1, -1, 0, 0, 1, 1, and 2, 8. So those 3 points in the middle that look linear, it's really not a straight line. It's going to curve in. It curves, it shimmies. It's not like there's hard angles, okay? So it's just going to go like this. And it's not great. I was going to say it's not awful either, but it's kind of awful. But I mean, it's good enough. You get the point. So that's what cubic looks like-ish. The square root function, which is the next one, is a little bit different than what we've done so far, okay? So if you were to go and try and put x equals -1 into the square root function, we learned that the square root of -1 is I, but there's no I on this coordinate plane. This particular coordinate plane uses real numbers only. It's called the Cartesian plane, named after Rene Descartes. And it just uses real numbers. And so there is actually no output or y value for -1, or in fact, any negative numbers for x. What that means is there will be no part of this graph that's to the left of the y-axis. None of those negative numbers will work. The first x value that would work, if you're going from left to right, is 0. And when you put 0 in for square root, that's okay. You can do that. That's just 0. So this is the first point on my on the square root function. No negative x values will have a point on this graph. And when I put 1 in, the square root of 1 is 1, so that point is 1, 1. And when I put 4 in and take a square root, it's 2. So this point right here is 4, 2. And so that's the shape of my square root function. Notice that here the domain is not going to be -infinity to +infinity. The domain starts right here. So the domain would be 0 to infinity. Same thing for the range. So that's the first of our graphs where the domain is not -infinity to positive. Does anybody need the screen up anymore? All right. Take a minute and look at these two equations. So the first one is the cube root function. It's the inverse of the cubic. And so we're going to see that it has this similar shape, but it's been rotated. So when you plug in -8 into this function, so my first x is -8, you're asking yourself, what times itself 3 times would give me -8? And that should be on the top of your head because we just did that over here when we were talking about the cubic. But right now we're going in the opposite direction. -2 cubed is -8. And so here, when we're doing the inverse, when x is -8, y is -2, because I'm taking the cube root. Similarly, when I put -1 in for x, the cube root is -1, and then 0, and then 1. And the cube root of 8 is 2. So we put those in. Oh wait, I did it totally wrong because my brain was on autopilot. So we still have this sort of snake-shaped thing. It's just turned. It's reflected over the y equals x-axis because it's inverses. And then square functions, probably one of the easiest besides the identity because it's a parabola, and we've done tons of parabolas in your math classes. You just plug those numbers in, square it. So -3 squared is -3 times itself is +9. -2 squared, 4, 1, 0, 1, 4, 9. And then we just plug those in and get our parabola. Which we knew we were going to get because x squared is a quadratic. And so again, fill in the domain, range, intercepts on your own. I know they're, well, okay, they're filled in for you on your copies. but you at least want to think about them and be sure you understand them. So again, here's the point of this packet of functions. We are going to be doing transformations of these parent functions, left to right, up, down, dilations, and rewriting their equations and all kinds of stuff this unit. The faster you can review these and memorize them, the easier the rest of the unit's going to be. If you put this work off and you think you're just going to wing it, you will be frustrated for most of the rest of the unit. Maybe not the first couple of days as we're easing into it, but after like Wednesday or Friday, you're just going to make your job harder. So here are the things you want to know. You want to be able to recognize the shapes, and you want to be able to remember these main ordered pairs, because those will be what we'll be using to make our transformations easier on us, right? And so that was just the first part of our lesson. The second part is practicing identifying features of these graphs that have been transformed. So let me go to the next part of the notes. If you're writing your own notes, you just need to put this title down. Your notes will say 1 here, even though mine say 4. So this is the title, Identifying Features of Graphs. And we're going to spend this first part, and those of you in class, if you want to move from your packet to the actual note page, we're starting that right now, is just review those basic shapes we just talked about and a little bit of vocabulary to go with them. So on this blank part of your notes, right here, we're going to review quickly those shapes we just talked about. We had the identity graph or function that looked like this. And it's pretty vanilla and doesn't have anything exciting to talk about it. So let's get to the next 2 shapes. We're just reviewing it. So the next 2 shapes I'm going to talk about are the ones that curve, or I'm sorry, are the ones that are symmetrical. We had 2 shapes that are symmetrical. One was the square function. And do you remember what the other one was? Perfect, thank you. Absolute value. And here's some interesting things that we can talk about for these 2. They have 2 features that we want to review. The first one is this special point right here where they change direction. Does anybody remember what those points are called? It starts with a V and then an E. Vertex. Wheel of Fortune. You could have put the X down and then the T and just waited for someone to guess. Those points are called the vertex of the graph. It's right smack in the middle of the graph, and it's where it changes direction and immediately goes opposite the other way. The other thing that happens when you have asymmetrical graphs like this is they have this special imaginary line that goes down the middle of both of them. Not actually drawn, it's just understood to be there. That line, if you remember, it's called the axis of symmetry, as opposed to axis of evil or something else, because it's math, not history. So for those 2 particular graphs, they have a special point called vertex and an imaginary line that goes down the middle called axis of symmetry, okay? For the 2 shapes that look like S's or like snakes, not S's, I mean kind of like an S. Stop talking. We had the cubic and the cube root. Cubit looked like this, and cube root like this. The special thing that we want to know about these shapes, they have a special point too. But in this case, it's not a vertex. It's just the point where it changes behavior. It doesn't change direction like on the vertex. It just changes how it's behaving. We are going to call those inflections. And then the last shape we had was the square root. And it has a special point, but it's even different than the other one, so we have a different name for it. And we're going to call it the initial point. And that makes sense, right? It's the point where it begins. So we had 3 points. We had the vertices or the vertex, inflection points, and initial point. So that's kind of vocabulary section for what we're about to talk about. What you'll notice on the rest of your note sheet, and before I change the slide, does anybody need the slide up anymore? Anyone in Zoom need the slide up anymore? Excellent. So the rest of the notes is a bunch of problems like this, where we have a graph that's been transformed, like it's been rotated, flipped, stretched, compressed, or whatever, from the parent functions. The first thing we did today were the parent functions, like the most basic form, before they've been altered at all. So the rest of the notes is graphs and equations for parent functions that have been altered. And all we're going to do is identify key features of them. And the directions for each section are identifying which features we want to identify. So in this problem, the first thing we want to do, part A, identify the function family. So looking at the equation and or looking at the shape, which of the original functions did this start out as? Is it identity, square, absolute value, cubic, cube root, square root? Which shape does it look most like? So a brave soul in class said square function. And that is what it looks like, right? So that's how it started out as just a square function before it got changed around. And then B is asking us for all kinds of information. B is very high maintenance. It says, describe or identify the end behavior, the vertex, the axis of symmetry, and any X or Y intercepts. So I'm just going to do those in the order it says so you know what I'm answering. So the first thing, describe or identify the end behavior. So I'm going to go look at the ends of the graph. On the left side, there's the left, there's the right. When we're talking about end behavior, we're talking about as it gets closer to infinity in either direction, what is it doing? And on the left end behavior, it's going, what the Y values are going down, and on the right, the end behavior, the Y's are going down. So here's what I'm okay with you writing is just 2 arrows, down, down, like the Led Zeppelin song. Other teachers, or if you see keys from other classes, Ms. Perez writes LEB for left end behavior, REB for right end behavior. REB always reminds me of Harry Potter, I think, because it's like one of the things, something about initials that sound like that. I don't know. So that's your end behavior, okay? The vertex is the point where the graph changes direction and goes the opposite way. And so in this case, that happens to be right here. That's my vertex. And I need the ordered pair for that, okay? And one thing you have to notice about this graph is it's skipping by twos. So it's 2, 4, 6, 8. Who do we appreciate? And then, so if it's skipping by 2, and this point is halfway between 0 and 2, right? That means the x value for that ordered pair is 1. And then the y value for that ordered pair is between 8 and 10 halfway, so it's 9. So we did the end behavior, the vertex. The axis of symmetry is an imaginary line, and you probably need to be reminded about how to write the equation of a vertical. So that's the axis of symmetry right there. That line, what's special about it is this. Every single x value on that line is 1. The y values change up and down, but x remains constant everywhere. And so when we go to write the equation of a vertical line, we're sort of describing that feature, the feature that x is always 1. And we write an equation of a vertical line like this. X equals. And that's how you write a line for a vertical axis of symmetry. And then the next part that B's asking us for is the x and the y intercepts. So that means where the graph crosses the x-axis and where it crosses the y-axis. So for the x-intercepts, the graph, meaning the blue parabola, that's what I mean by graph. I don't mean the grid or coordinate plane. I mean the actual shape that we're talking about. Where that crosses the x-axis is in 2 places, here and here. And so we need to write those as ordered pairs. The one on the left, remember this is going by 2's. The one on the left is -2, 0, because it doesn't go up or down at all. And then the one on the right is 4, 0. And the y-intercept is where that blue graph crosses the y-axis. And the biggest mistake students will give me is they think it's at 1, 9 again. But that's the vertex, okay? So look at where does the blue shape cross the y-axis? And that happens to be right here. And that's the ordered pair that we want. It's 0, 8. And then C is asking us for the domain and range. So the domain is all the x values that have a point on the graph. It's the left boundary and the right boundary. So it's left, you're doing domain left to right. So the left boundary, since it's going to keep going forever and ever and ever, the left boundary is actually negative infinity. And the right boundary is the same. It's going to go down forever and ever, but you know, it's very slowly also stretching out to the right. And so the x goes to positive infinity. The range, however, is the y values from least to greatest. So it's bottom to top. So I'm going to erase all this craziness I have going on here so we can see it better. Erase, 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 erase. More erasing. Some more erasing. So when you're trying to find the range is the bottom least value to the top most biggest value. But when you're looking at the bottom, it's going down forever and ever. So that means the lower boundary is actually negative infinity for the range. And the upper boundary is 9 right there. It will never go higher than 9, but it does include 9, so that gets a bracket. And what I want you to do is take a few minutes to try the rest of the problems, and then I'll show you the answers. My only concern is anyone who's taking their own notes in Zoom, do you have the problems up on your device? Does anybody, you do, okay. So if you're doing your own notes on Zoom, we have the blank note page up from your Google Classroom, from your stream announcement, and just try the rest of the problems, and then I'll show you the answers in just a few moments. If you're watching the video asynchronously, please pause right now, finish the notes, and then come back and check your answers. Okay, so hopefully you finished the rest of the problems. I'm just going to scan through the slides and show you the solutions to the rest of them. Notice that for the end behavior for the square root function, I put that the left end behavior DNE means does not exist, or maybe you put none or something like that. Yeah. So there's that slide. Pause if you need to see it longer. I'm going to move on to the next one. Here's the next slide. Pause it if you need to see it longer. And the next slide. Pause if you need to see it longer. And I think this is the last one. I'm not sure. Pause if you need to see it longer. Okay, there you go. And there is a practice worksheet to go with the lesson. There's no grades today in the homework. You can self-check it with the key in your stream announcement.